Welcome, AP students, to the discussion on what is PES, photoelectron spectroscopy. So today in class, we were introduced to it a little bit. There's another video attached to your assignment that goes into how do we interpret PES spectra. I'm going to do that a little, but sometimes it's nice to have a different person explain it to you from a different perspective. So PES is a way to measure how much ionization energy will be needed to remove an electron. And it's a very specific type of spectroscopy. So if you remember from the last lecture, and I'm going to just screen snip this so that we can watch it. I can write on it. So from the last lecture, we talked about making positive ions. And positive ions mean that you are removing an electron. This leaves. So PES measures if you want to take away a specific electron, how do you do that? Like how much energy would you need? How much energy would you need to remove the first electron from sodium? If I wanted to go further and go from sodium plus to sodium 2 plus and remove another electron, how much energy? There's an energy difference to go from here to here. There is a change in energy. You have to put, well, that's supposed to be a delta. You have to put E into the system to get that to happen. Right? So PES is a way of measuring what that E is, so you know exactly how to hit that electron, that atom or that ion, to remove more electrons. So that's what PES is. I'm going to go through the background on PES. The main thing you need to know is a little bit of principle on how it works, which is what I'm going to get into now. You don't need to know all the different physics behind it, but you have to be able to interpret PES spectra. Okay, that's a big thing. You have to be able to justify your answers. You have to be able to talk about Coulomb's law. Those are the things that you have to pull out of this as you watch these slides and we go through what we did in class again. Right, so if you felt comfortable with what we did in class and you think you've got it, this will always be here as a resource. You can go on to the one that talks about interpreting spectra. If you want to listen again and say, Jay, I want to go over this again because it didn't all click, then just continue listening. All right, so PES spectra came about from Hertz, okay? Familiar, right? We have a unit called the Hertz, and of course that was because we named it after a famous scientist who maybe at the time wasn't completely famous. So it's a little hard for me to write today. So let's do this. Hertz. And then stuff that Einstein did. So what happens is that you take, and this is supposed to be nu, right? So this is energy, H nu. The people that made this slide, and I couldn't edit the picture, used N for nu rather than the Greek symbol for nu. So this is a particle here with a specific energy that's coming in a waveform and hitting a surface. Okay, so in a way, the photoelectric effect is what gives things shininess. Right? So we have shininess. We talked about this before, that if you can hit something with a particular electron, particular energy, you're going to have an electron leave. So knowing this principle and knowing that you have to have an electron that has kinetic energy, and you have binding energy, which is essentially, in a way, potential energy. Okay, if you hit it with enough energy to overcome those forces, you will get this release of the electron. And that allowed them to study matter more closely, because now you can give an energy assessment to what's going on. So essentially, you hit surfaces with an energy, you hit atoms with an energy, and that energy, if it's just the right amount of energy, will eject an electron. Now, PES, photoelectron spectroscopy, right? So you're going to hear the term PES, PES, PES. So PES is a particular analytical method. Okay? It's an analytical technique. There's many analytical techniques, which we will talk about at the very end of this. You have to keep which technique you need to use when straight, which is why I give you an organizer that tells you what it is and when to use it. And you have to keep that straight. Okay, so there's many, many different types of spectroscopy. Most spectroscopy use this thing called resonance transition. In other words, you have an electron at this energy level, an electron at that energy level, and to go between these two levels, it's a transition. And this transition is of a certain energy level. So when it says you're in resonance with that, that's what they're talking about, that transition. So they also will measure whether you are absorbing or transmitting photons. And photons can be like what we can call as light. A lot of times a photon, we're talking about one individual photon, but you hit it with a wave of light. And remember, a photon can be just a particle or it can travel in a wave. And that's where I say to you, chemistry is physics, and that's the physics coming into it. So most of you have not had physics, so it's a little bit weird to think of this concept. But all of you did either accelerated 7th and 8th grade science together, or you did regular 8th grade science, where you talked about waves, and you talked about light, and you talked about movement of those. You should have. At least you did when I student taught it. So, and I student taught here in New Hartford for 7th, 8th grade accelerated, and then 7th grade science and 8th grade science. Not earth science, though. Just regular 7th, 8th grade science. And then a combination of the accelerants. Okay, so realize, too, that in order to optimize finding this transition value, they do this thing called scanning the energies. So they literally go from a blue light all the way to a red in what they call a sweep, and they scan all the energies. And they use all of them, and then you get responses, and you can tell stuff about the atom. Photoelectron spectroscopy is very specific. Okay, it hones in on and focuses on a particular energy value. Now that energy value will end up being different for each atom because it has to do with Coulombic attractions. So this photoelectron stuff has to deal with our wonderful thing of Coulombic attractions, which is why I added that video in. Now these videos that I added in, other than the TED Talk on Mendeleev, comes from AP Central. Okay, so when you go to your AP classroom, I assign them and they pop up on your AP classroom. Right, so when you click on the link, you will have to sign in to that AP classroom. So it focuses on a particular electron, so it is going to focus on just the energy to eject that particular electron, not a sweep. And that's where it's a big difference. And then when they're ejected, the way they determine this is that they measure the kinetic energy flowing out of the electron because there's a relationship there. And that's why they call it a monochromatic photon source. It is one wavelength or one frequency that equals a particular E value. Right? And that's the difference. Okay? If I want, I'm going to do generic. I hate these models of the atom because it makes you to believe that Bohr is correct, but it is extremely difficult to draw a 3D model of the atom. So we say, okay, we have our nucleus, and then we have our little electrons going around the outside. If I want to target, I have 2 electrons here, and I have a couple electrons here, I'll just throw them out. If I want to target this individual electron, it is a certain distance from the radius, a certain distance from the nucleus. So that has a certain E to it. If I pull this electron out and I go, I need to remove that, I will have to hit this atom with that particular E value that represents that distance. I take an electron out, the structure changes. These collapse in a little, and now, like this guy, if I went to go get him, would have a different value. The closer you are to the nucleus, the more E it takes to remove the electron. Please, this can get confusing, so you've got to keep this straight. The farther the electron is on its distance, this electron possesses more E in itself as it exists in the atom. Okay? It possesses more E. It itself possesses more E. I'm trying to figure out how to make this very clear. Okay, this electron possesses itself, what it owns, what it has, more energy. It's at a higher energy than electrons closer to the nucleus. But its distance, r, is greater, so takes less E to remove it. Notice the difference between possessing energy and needed to remove the electron. Two different concepts. Don't get them confused, because that will mess up your answers for any PES question, because PES has to do with the closer you are, this R gets smaller. Because it gets smaller, the Q1 over Q2 over R squared gets bigger, so you need more E to eject that. To get that out, you need more E. It itself contains lower energy in a spatial relationship where it resides. It's almost at a lower rent district because it's near this central, busy, congested nucleus, right? These are the beautiful burbs out here, way out that way. So your land is more expensive and you have higher energy to maintain your land. That has nothing to do with how well you're attracted in here. Okay, so just think about it in terms of closeness means you're held on tighter. To remove you takes more. But you're at a lower energy yourself if you are the electron. All right, so let's move on. This is going to be just a real brief description of how this works, the ionization and what states you go through as you're going through the instrument. You do not need to know about going through the instrument and detecting. What you need to know really is how to interpret spectra. If you're really into this, there is a PES lecture that's given by Intro Chem at MIT. And I think this video is still available, and you can upload it and watch it if you're really into the spectroscopy part of it. If you're not, don't worry about it. It's the interpretation that is important. So I'm going to quickly go through, very much like looking at mass spec. You make an ion, and the ion travels, and then the ion gets detected, okay? And really, what ends up happening is your electron gets detected. You whack out the electron, and it goes through its deflection, and it gets the detector, and once it gets there, they measure how much energy that electron has based on the distance it traveled, the time it took to travel it. They know the mass of the electron, so they do physics calculations to calculate how much energy that electron is traveling, right? Basically, that's how it works. So let's look at interpreting spectra. These are different ways of presenting spectra, and you'll see some more in the AP video. So it is measured with respect to energy. Now, these are reverse scales, and sometimes they do this. Now, if you look at the scale, the higher energies here, lower energies over here. The reason why they do this is higher energy is closer to the nucleus, oops, yes. Lower E, farther out. And guess what this is based on? It is based on filling. Now, now, guys, because we're a combination of remote and hybrid, and some people 100% remote, normally you really need to have that filling pattern down. Okay, so some of you were checking your notes when you took your notes, and I know you want to be sure that you knew it and that you were writing the correct things. I can't stress enough to you. Right now, I just got an email a couple days ago, and I haven't addressed this with administration. AP is saying if your school is open, okay, even if you feel you're 100% remote, if your school is open, the AP test will be administered in person. Okay, this has been on my chat line for AP Chem for a long time. And it says, you need to go to your school and take your test. I have no idea if they're going to be hardline about this and say, in May, we're doing it this way. Right now, this is their mantra. If your school is remote, unclosed, then you have to take it online. And I don't know how they're going to end up doing that, because then you have access to your notes where somebody else does not. Okay, so I'm not sure how they're justifying all of this. I can tell you this, though. You will not have the time to look up anything when you are taking that test. Can't even stress that. Okay, you have a minute and a half for every multiple choice. A minute and a half. And some of them take more than a minute and a half. Some take less. If you're screwing around with your notes trying to look up things, you are not going to do well. And the same thing with your part 2. You get like 20 minutes for one, 20 minutes for another, 7 minutes for one, and you need to know it. It's like bang, 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 bang. So make sure you've got this memorized, because this is, you're going to have some PES questions, you're going to have filling questions, you're going to have Aufbau questions, you're going to have Hund's rule questions. So you need to know that. Okay, so how do we look at this as based on filling? Well, if you are in an s orbital, it's closer than a p. If you're in the first level, you're closer than higher levels. Well, that's closer. So if you look at your filling, your 1s, 2 will have the highest E. And then later ones, let's say if I had something that's a 4p6. Oops. Let me clean that up. You got a 4p6. These guys would be lower E, to take and hit them and remove them. So you have to look at your graph. Where's the highest E? Where's the lowest E? Read the values. Okay, so I can't stress that enough. Read your scales. Where is highest E? Where is lowest E? Okay, highest E is going to be s orbitals. So if we look at the first slide on the left, the first picture on the left, you notice this is higher E, right? 84, higher than 208. This is my 1s, then we go 2s2, then we go 2p6. Relative intensity. I draw a line across here, and then I double that. That's about here. And so if I look at this, this is 3 times this height. Say this height compared to this height. That's about 3 times. So if I'm filling, I should have 2, 2, 6. Now there's a difference between sodium and neon here. And the reason why is sodium has more protons. It has more charge. What's Coulomb's law? The charge of one times the charge of 2 over R. This is going up. The attraction is getting stronger. This goes to higher energy because these are closer than those. It gets pulled in. And I shouldn't say pulled in. There's a stronger force. So you have to overcome that force. And that stronger force has to do with more protons in the nucleus, right? Stronger coulombic force for sodium because of the added protons. And electrons too, because they both go up a number. Okay? Gotta remember that. So if I look at the next material that's there, again, highest energy, that'll be the 1s2. Then I go and look, and what's my next way to fill? 2s2, 2p6. These tell you what they are. But if you think about it, here's, this has 1s2, 2s2, 2p4. Relative intensity to height. See how this is shorter than that? It's relative. They don't really tell you how many electrons are in it. Sometimes they'll be nice and they'll actually say 2, 4, 6, but usually they don't. And if we look at carbon, 1s2, 2s2, 2p2, right? Yeah, 6, 2p2, right? And see how it goes down in intensity? So when you get a spectra, you start from the highest energy level and you label it 1s. And you have to look and see what's the height of it. You know, usually they give you a deeper spectra than just having only the first energy level. So they don't give you hydrogen and helium. So then you start your filling, 1s2, 2s2, 2p6. But you got to look at height because they could leave you off at 2p4. You know, like oxygen. They could leave you off here and you only have 3 peaks. So it's all based on filling. Okay, and the final thing we talk about is the different types of spectroscopy. We haven't been exposed to all of these, okay? You've essentially kind of been exposed to 2. One of them you didn't know about yet. But when we look at trying to find out your PES, right, it's considered X-ray because of the type of energy that you use. You use high energy, right? This gives you the structure of the atom, the location or the E for the electrons to remove them. Please understand, they call it ionization energy because you're kicking out an electron, but it doesn't mean that you're taking off the first electron, the second electron, the third electron. You can take out any electron in that whole structure as long as you know its specific E. It's like searching somebody because you're mad at them. This is a horrible analogy, but it's the first thing that can come to mind. You are mad at a particular individual and you search them out to hit them. Okay? You plan, you put all this energy into it to get back to them, which I never recommend you doing. Right? And that E is specific for your feelings towards that person. So in the PES, it's specific for each individual electron that's in that structure. Okay? Now, we've kind of done this. We've done it a little bit because this is like a bright line spectrum. It deals with a whole bunch of energy waves. So we go from 400 to over 710 in our ultraviolet range. And we hit it, and it absorbs energy, and then it relaxes down, and it gives off those colored lights. And that's the type of spectrum that those spectrometers measure. They measure that excitation and relaxation over the span of that UV-Vis range. Right? We can use visible light as well, because that'll also be an energy transition. But we usually use infrared and that type of thing. Well, actually, I have to be careful because infrared is infrared. It's IR. We will talk about IR later. IR gives you, in fact, we'll talk about it on the next topic. IR gives you very specific structural information. So does NMR, which is a very low frequency, right? Very, very low. So NMR doesn't even expose really the analyst to anything bad. It'll mess up pacemakers. It'll mess up anything. I think it probably even mess up if you have like a cochlea implant because of the radio frequency. All right, so on the next slide, that is that picture. Now you can look at it in color, and it tells you where frequencies are, and it tells you where things happen. So we use that ultraviolet invisible wavelength to do the spectroscopy, usually even this, like we just scan those wavelengths. We're going to do some when we get to solutions. We do what's called Bayes' law, where we will use a colorimeter. For those of you at home, I'm just going to end up giving you data, but if you are in class, you will see how to use it, how to program. I have to show you how to program it because they took on my computers. But we'll still look at it. I'm going to have to fight for that too. Alrighty, so that is PES in a quick nutshell.